Is it recording and is it in focus?
Yeah, a little high.
A little high. All right. All right. So is it getting most of it? Excellent. All right. So this is the last lecture of Math341, lecture 34. I want to give you a sense, again, of where things go, what are the technical issues, and how do we try to resolve them. So what can you use all this stuff for? Okay, so the general formulation is you have some system, and you observe values, and you want to understand what rules govern the spacings between these events. So we've talked a little bit about spacings between events before. My main areas of research are energy levels of nuclei, eigenvalues of matrices, and zeros of L functions. It turns out the same mathematics describes all three of these. Anybody know what company is one of the best companies in the world for understanding spacings between events? For understanding wait times.
Wait times?
Wait times, not like that, but how long you have to wait. Yes? Disney. Disney is outstanding at managing wait lines and knowing how long the wait will be at various places. And they do a lot of stuff to constantly be updating in real time what their estimates are. A lot of times, if you think about how lines are managed, do you have one massive line, which everybody goes into, and then first available teller, or do you have four lines, and then you have people who have line envy? I chose the wrong line again. And this is the time of year where there is a lot of line envy. Now, in some situations like a supermarket, when you have a lot of carriages, it's actually very useful to have different lines and not have one massive line in terms of just how the space of the store is done. But there is a huge amount of research that's done in terms of managing lines. The average wait time will be the same, but the variance will be very different depending on whether or not you have one line or multiple lines. And so there's a lot of great work and stuff like this. So there's often three different things you need to do. You have to figure out what's the right scale for events. You need some kind of explicit formula relating what you know to what you want to know. And then you need some kind of averaging formula. So this is going to be a very brief introduction. I want to make sure we have enough time to do the evaluation forms. If you're interested in more details, I'm happy to chat. And again, these are related to projects students can work on at small this summer. All right, quick review of linear algebra. If you have a non-zero vector, it's an eigenvector of A with eigenvalue lambda if A equals lambda V. So essentially, it means you've just rescaled the length of the vector when you apply the matrix. Typically, when you apply a matrix, you change both the magnitude and the direction of a vector. It's very convenient if you only change the magnitude. So for an example, the matrix 1, 2, 2, 1 has two eigenvalues, 1, 1, and 1, negative 1, with eigenvalues 3 and negative 1. It turns out the eigenvalues for a lot of matrices really encode what's going on. And a lot of times the actual eigenvectors don't really matter that much. They're going to appear differently depending on what coordinate system you choose. We've seen this with ellipses before when we did Monte Carlo, that depending on your perspective, it could either be a hellish equation where it's not centered around the coordinate axes, or if you just rotate, now all of a sudden things align nicely. So typically, if you have a real symmetric matrix, one of the big results in linear algebra is the spectral theorem, that there is a nice orthonormal basis where in that basis the eigenvalues determine the matrix, where in that basis the matrix becomes diagonal. And in physics, it turns out that there are a lot of times where we can approximate things with a matrix, and the eigenvalues of the matrix are the energy levels. I'm not even going to bother going through this slide. We've seen it too many times. Standard examples, exponential, normal, uniform. We'll look at a bunch of these later. The key concepts, we know what the mean is, we know what the variance is, we know what the kth moment is. All right. We know that if your function is nice, then your Taylor series should determine you. Just like if your probability distribution is nice, your moments should determine. There are technical conditions lurking behind all of this. The goal of today is not to delve into those technical conditions, but to just let you know that they exist and give you a sense of what kind of problems can you attack, what are the issues that arise. The hope is that if we can determine moments, we can then determine a probability distribution. All right, so I'm going to talk a little bit about classical random matrix theory. It began with the statisticians in the very early 1900s, but then really kicked up with the physicists in the 1950s, and then it was turned out to by a freak accident of people just talking, so what are you interested in? In the 1970s, it was realized it applies to number theory as well, to primes and the Riemann zeta function. So classical mechanics. If you have 1 point mass in the universe, it's boring, we know what goes on. If you have 2 point masses in gravity, nothing else in the universe, it's boring, we know what goes on. As soon as you have 3 points in general configuration, you have chaos. We cannot write down even explicitly what happens. It is possible that Pluto could wander off from the solar system, trillions of years from now. Or we might not be able to determine Pluto's orbit exactly, but we might be able to bound it and say, I don't know exactly where it'll be, but it'll be in a certain range. But we can't solve 3 point masses in general configuration under gravity exactly. So imagine you have something like uranium, where you have over 200 protons and neutrons, and the interaction is far worse than gravity. If we can't even do this, we have no hope of this. Given that a lot of this stuff was happening in the 1950s, you can probably understand why people were quite interested in understanding things about uranium. So I love how nuclear physics works. The way you get information is you shoot high-energy neutrons into something and see what comes out. So a good way to understand this is, imagine you want to figure out how a grandfather clock works. So you take 2 grandfather clocks and you accelerate them to 0.99 times the speed of light, and you smash them together, and you see what comes out from the destruction. And you use that to determine the inner workings of the grandfather clock. This is essentially how subatomic physics works. This is the fundamental equation of physics. The Hamiltonian matrix of the system, psi of n is the energy eigenstates, En is the energy eigenvalues. This is a linear algebra problem. There are only 2 things that prevent this from being a linear algebra problem you would see in Math 250. The first is H is infinite by infinite, and I believe most of the matrices you've looked at have been finite. And the second is we don't know any of its entries. Other than that, you could do it in 250. So given that it's infinite and we don't know any of the entries, we're in trouble. So how do we attack something like this? How many of you have seen thermodynamics or statistical mechanics? Right, not too many. So if I want to calculate some macroscopic quantity like pressure, I want to look at how many air molecules hit the board in a certain amount of time. And if you want to make life simple, we'll assume all molecules are traveling at the same speed, and you're equally likely to be going in either direction. What I could do is I could look at one possible configuration of molecules and calculate the pressure. Then look at another configuration and calculate the pressure, and average over all configurations, and now you can begin to see probability emerging. Anybody know roughly how many air molecules we have in this room? Within 5 orders of magnitude.
Around 10 to the 28.
Yeah, around 10 to the 28 should be safe. There's at least a mole, which is 10 to the 23. So this gives you from 10 to the 23 to 10 to the 33. We cannot solve a system with 10 to the 23 to 10 to the 33 objects. But a lot of times we can mathematically calculate these averages. And so rather than trying to deal with an exact solution, we average over all possible configurations, and then we just pray that the configuration in this room is close to the system average. This is essentially the essential limit type theorem, that the average behavior is going to be a good approximation for the typical behavior. All right. In nuclear physics, it turns out the matrices we look at are often either real symmetric or complex summation. For today, I'll mostly focus on real symmetric matrices. I'm not going to get into connections with number theory, but if people are interested, I will leave some slides there and always happy to chat. So I take a real symmetric matrix, so A equals A transpose. So Aij is equal to Aji. And what does it mean to choose a matrix at random? Well, it means I choose each of my entries independently from a fixed probability distribution with density P. There are other ways you can choose matrices. This is a nice one. And I'll be careful, I will only choose the independent entries. If I choose the upper right, since it's real symmetric, I know the bottom left. So I'll take a product 1 less than equal to I, less than equal to j, less than equal to n. How many ways can I choose 2 elements from n? That's n choose 2. It's on the order of 1/2 n squared. So that's roughly how many independent entries there are. There are only n eigenvalues. So there are far fewer eigenvalues than independent degrees of freedom. So the eigenvalues is only a small subset of what I need. The rest is coming from just orienting the eigenvectors. More explicitly, I can talk about what's the probability of choosing the matrix A where each Aij is in some interval. Well, that'll just be the product of the probabilities that xij is between alpha ij and beta ij. So all of the probability stuff we've been doing allows us to handle stuff like this. All right. So we want to understand the eigenvalues of A, but it's the matrix elements that we know things about. So I want to remind you of one of my favorite lemmas from linear algebra, which you either have heard of and thought, who gives a damn, or didn't even hear of in your linear algebra class. It's the eigenvalue trace lemma. How many of you have heard of the eigenvalue trace lemma? How have you ever had any idea why we care so much about it? When you first see it, it's like, all right, the trace of a to the k is the sum of the eigenvalues to the k. So typically you do it when just k equals 1. The trace of a is the sum of the eigenvalues, but you can generalize this. Why is this useful? Well, I want to understand the eigenvalues of the matrix. This relates the eigenvalues of the matrix, which I don't know, to the matrix elements, which I do know. And in fact, the trace of a to the k is a nice polynomial. So one of the points is to see how your different math classes talk to each other. Linear algebra is a prerequisite. With linear algebra, there's a lot we can do now with probability. What do the lambda to the k's look like? What does this look like on the right-hand side? What if I multiplied by 1 over n? So I put a weight of 1 over n at each eigenvalue. So if k equals 1, it would look like the mean. This looks like the kth moment. Or it's the kth moment up to just putting in a weight of 1 over n. So the whole point is, if we understand the moments, we understand the probability distribution. The kth moments are now related to the trace of a to the k. The trace of a to the k is a polynomial in the matrix elements. We know how to do stuff like this. And this gives you a sense of what kind of problems we can attack. So to just make things a little bit more explicit, delta is going to represent the Dirac delta functional. Essentially view it as a unit point mass. All of your mass is located at the point x naught. So if I integrate any function against the delta function, it just returns the value of the function at x naught. So your density is 0, spikes up to plus infinity, and then is back to 0 as you continue down the real axis. You can, of course, argue that, well, that's not really a function. That's why we're saying functional. If you don't like this, you could take a Gaussian with extremely thin width, with extremely small variance. And if you take the limit as the variance of the Gaussian goes to 0, it's going to spike up and become the delta function. So you can actually do this through continuous functions if you would prefer to do it that way. So to each a, we can attach a probability measure. And so what we'll do is we'll take our eigenvalues, and it turns out it's convenient to divide them by 2 square roots of n. And by dividing by 2 square roots of n, we're going to have something that will have a nice limit as n goes to infinity. The root n is the important part. The 2 is just so I can say circle rather than ellipse later. That's not as important. But you want to understand what is the behavior of your system as your parameters grow. That's the key observation. And so if I just integrate my counting function from a to b, it's going to just count how many eigenvalues I have, such that the normalized eigenvalues between a and b, or more generally, if I integrate against x to the k times this, I'll get back the sum of the eigenvalues to the kth power, suitably normalized, and that's just the trace of a to the k. So the idea is we can calculate the average moments. And in fact, we can even calculate the variance about the average moments, and then use this to show that a typical matrix is actually very close to the system average. So the idea then is, which matrices do we want to look at? So the big result is Wigner's semicircle law. It says if you look at real symmetric matrices, then almost all matrices in the limit will have their distribution of eigenvalues being a semicircle. So the first I want to do is I want to give you a sense of the correct scale. And again, part of this is to show you all the different ways the central limit theorem can help us. So the trace of a squared is the sum of the eigenvalues squared. All right, so the trace of a squared is the sum of aij, aji, that's aij squared. I'm going to choose my random variables to have mean 0, variance 1. I'm going to standardize like this. Well, if these have mean 0 and variance 1, aij squared, the expected value of that is just the variance, which is 1. And I have n squared of them, so this should be of size n squared. And you can even talk about what you would expect the fluctuations about this to be. Much smaller, much lower order. So we expect the sum of the squares of the eigenvalues to be of size n squared. We have n eigenvalues, So we expect the typical eigenvalue to be of size square root of n. So if I give you a matrix of growing size, we expect the eigenvalues to grow like root n. So this is the power of the central limit theorem. It tells us immediately what's the right scale to study things. Right. So we now just need to calculate the average kth moment. And so to calculate the average kth moment, we just take the trace of a to the k, we multiply by our probability density for the matrix, and then we expand out the polynomial and we integrate. And at this point, it's no longer probability. It now becomes combinatorics and number theory as to how do you actually compute that. I'm not going to go into too much detail on this. I'll just go through a couple of slides. There are slides with far more details. Here is an extremely misleading example. Let's calculate the second moment. So if I calculate the second moment, I've got aij squared. I've got a finite sum. I can move the finite sum out of the integral. And then I have aij hits paij, which is one integral. And then all the other integrals are like this. Well, since these are probability distributions, these all integrate to 1. And because the variance is 1, these all integrate to 1. And so the ends cancel and you end up getting, I think, 1/4. Looks very easy. The reason it's very easy is because we only have one term here. As you go further and further, it becomes a little bit more important in terms of matching. Just for some numerics, here's looking at 500 Gaussian matrices of size 400 by 400. The red line is the theoretical curve. You can see, very good fit. Here's one of my favorite distributions, the Cauchy. Why do I like the Cauchy so much? What's so nice about the Cauchy? This is also meant to review the semester, right? These are not just application lectures, but it's a chance to review all the stuff we've done. What's so great about the Cauchy? It doesn't have a mean. Some people will argue with you on that, and they'll say, yeah, but come on, integrate symmetrically. So what would you respond to them?
Then just integrate, just shift the center over and you get a different answer. So if it depends.
But they're not going to let go. They're going to argue with you to the death that there is a way to interpret the mean.
Then just go faster on one end than the other.
No. Well, it has a median.
Yeah.
So they'll say it has a median. It may not have a mean. It has a median. But what can you then get them on the Cauchy? What does it not have? Yes.
It has infinite variance.
It has infinite variance. The Cauchy has infinite variance. In the Wigner semicircle theorem, we often talk about a nice probability distribution. Wigner says if you have mean 0, variance 1, and finite higher moments. This doesn't even have mean 0, but you can maybe push it. It has infinite variance. Do you expect the Cauchy to satisfy the semicircle law? And the answer is no. Not even close. And it doesn't just bump up over here. This is just all of the normalized eigenvalues that are this large or larger. It has remarkably different behavior. There's a lot of stuff you could do. It turns out if you look at spacings between eigenvalues, the Cauchy and the real symmetric matrices have the same behavior. And that spacings between events is a more fundamental quantity than counting how many events you have. I want to give you a little bit of a sense of how you do some of these calculations. So here is looking at Toeplitz matrices. So Toeplitz matrices are constant along diagonals. And I want to calculate the density of states. And so we have a normalized eigenvalue measure. We put our masses. It's the kth moment is related to the trace of a to the k. It turns out it's not hard to show that all the odd moments is 0. So I'm not going to really work on that. We're going to look at the even moments. And all that really matters, because the matrix is constant along diagonals, is do I have two things that are on the same diagonal? So instead of writing aij, I'll just write as bi1 minus i2. It turns out if these are not matched in pairs, because of the power of n I'm dividing by the number of tuples, it's a lower order contribution. And again, I don't want to go into all the details here. If you want to, happy to chat, happy to show you the papers. I want you to get the broad brushstrokes. If they're not matched in pairs, it's a lower order contribution. So everything has to be matched in pairs. If something is unmatched, it's mean 0, so it'll immediately vanish. And it turns out if something is matched in a triple or higher, it's a lower order contribution. It's too unlikely for all that to happen. So you have to look at how many ways can you match things in pairs, and there's a bunch of combinatorics to do. I'm not going to go through all that. You can show that it's bounded by the moments of the Gaussian. I'm going to skip all the stuff over here. I'm going to skip all the stuff here. When you look at this, does this look like a Gaussian? When we did our simulations, we at first thought it was a Gaussian. It turns out it's not. The fourth moment is 2 2/3. It's a little bit less than the 3 of the Gaussian. We in another group were independently investigating this at the same time. And it's very easy to be misled. When I shared this plot with one of my colleagues, he says, oh yeah, it's a Gaussian, here's a heuristic as to why. Be very careful about data. When you look at this, can you really see that it's not behaving correctly? Well, now that I know it's not a Gaussian, yeah, it looks like it's decaying a little bit too rapidly. But if you're in the mind to think that there's a Gaussian, then you will see a Gaussian there. And two groups independently saw this. Think of the story I sent you from Asimov, The Planet That Wasn't, where people were trying to find the planet Vulcan between the Sun and Mercury. If you think it's there, you will see it. So this is a really good warning to end the semester with. All right. We looked at block circulant ensembles. So these matrices are a generalization of toplets. Instead of being constant along a diagonal, it has a pattern that repeats every so many. So this is repeating every 2. You could repeat every 3. If you repeat every 1, it's the toplets. And you can write down explicitly what the formulas are. It turns out that to solve this, a lot of topology comes in. And it turns out you can look at identifying sides on a polygon. And if it's not matched properly so that it folds in, then it will not contribute. So there's a lot of beautiful topology. And if you like topology, you will enjoy this paper. These ones won't contribute. This is the only one that will. It turns out it's related to the number of pairings of edges on a 2K-gon giving rise to a genus G surface. You might notice that there's going to be some convolutions that will be coming into play. We've talked about using the characteristic function, which is not the moment-generating function. It's not e, the expected value of e to the tx, but e to the itx, which always exists. You can do calculations like this, and you can get a closed form expression for the densities. It's very unusual to be able to get a closed form expression for the densities. This is the case where it's toplets, and we keep increasing the length of the periodic block. What does this seem to be converging to? Not a Gaussian. The semicircle. So if you go back and you look at the density, not immediately clear that this is going to look like a semicircle. There's a lot of really nice special function analysis that goes in here. Professor Stark from physics joined us for the analysis. But in the limit, it will converge to the semicircle. For any finite period pattern, it's going to have infinite support. It's going to go off to plus or minus infinity, but it's going to start decaying very, very rapidly. And it's amazing how close the fluctuations are. If you look at this, we'll go back a little bit earlier, you could see it really is picking up the dips and whatnot. So over the years, I've had students study a lot of different ensembles of matrices. I just want to end with the checkerboard ensemble. Right. Has everybody seen a checkerboard? All right. So what we're going to do here is this will be a checkerboard, but now it'll be every 3 rather than every 2. You can choose how long you want to wait. And so what we're doing is every 3 we put in a W, YW. Yeah, it's either for Williams. We'll officially say it's for the weight, but it's for Williams, right? So we'll do a W. You stick these things into your papers. So we'll do a W every 3rd, or you could do a W every 4th or every 5th, and you can ask what happens to the behavior. And it turns out that almost all the eigenvalues obey the semicircle law, and there's a small little blip that goes off to infinity, and the number is related to how many steps you have to wait before you get the next W. And so you can see it pushing further and further out. And so to keep it all on the same scale, this is getting more and more compactified, but it is still the semicircle. And this introduces a lot of very challenging probability questions as to how do you attack something like this. So unfortunately, these eigenvalues of size n, these eigenvalues of size root n. If we try to use the method of moments, it turns out the moments become plus infinity. And because they're plus infinity, we can't use the method of moments. So we need a way to isolate just the eigenvalues here or just the eigenvalues there. And so I will end by just introducing a weighting function. So this is a nice function, x to the 2n, x minus 2 to the 2n. Where is this function largest? I'll accept 3 answers.
And the magnitude of x is really large.
So one is when the magnitude of x is really large and positive, or really large and negative. And there's one other point where you could argue the function is large. Around 1. And so by using this, I can actually concentrate my vision on just the eigenvalues near 1, because if you move just a little bit away, as n gets very, very large, it's going to really decrease the weight. So this is a weight function. And so this is, plotting it out now, looking at 4 to the m goes from 0 to 5. And you can just see how rapidly it's dropping off by the time we get to 4 to the 5th, also known as 2 to the 10th. So only the eigenvalues in the blip would be counted when you do something like this. And it turns out these blips have, fascinating shapes. So, again, this is a very fast introduction to random matrix theory. This has been used to model things from energy levels of heavy nuclei to zeros of L functions to wait times for bus routes in cities where the drivers actually have freedom in terms of where they want to stop. It's amazing how many things can be described by the mathematics like this. There's a lot of challenges. How do you focus on the object you want? You need to have some kind of formula that you can work with. If we didn't have good averaging formulas, it wouldn't matter if I had the eigenvalue trace lemma to convert sums of eigenvalues to sums of the matrix elements. I've got to be able to work with the sums of the matrix elements. And because those are polynomials, we can do things. Things are much harder for L functions. We don't have as good formulas for that. And this is why the number theory results are not nearly as good as the results in random matrix theory. Various distributions will have similar behavior. The Cauchy distribution will violate some of the assumptions, and not surprisingly, will have different behavior in different settings. All right, and then the last thing is I really want to emphasize here, the final point for the semester, is be careful about being misled by data. It is very easy to look at something, especially if you think you know what the answer is, and then see this as reinforcing your belief in preconception. So I will end with warning you on that. Let me hit stop.